Today we're going to be discussing evaluating algebraic expressions. And in order to evaluate them in the correct order, keep in mind that you already did a lot of work understanding the story of how an algebraic expression should be evaluated, even if you weren't thinking about it in that language yet. If, for example, I were to write 7 minus 3x squared, you would know from your work on the story of how algebraic expressions go is that you want to follow order of operations where you first want to square x, aka multiply x times itself. Then you would want to multiply by 3 because that would be the next thing that you would do order of operations wise. And then you would subtract from 7. That was previously when we left x just as a variable, meaning that it's an unknown quantity that can take on any value. That would be how you would leave the story as. Now if I actually gave you a value for x, you could evaluate the algebraic expression. If, for example, I said let x be 2, you would then rewrite this algebraic expression with a 2 plugged in for x, and then you would exactly follow these steps in terms of order of operations. First, you would square x, square 2, 2 times 2 is 4. Then you would multiply that value by 3, 4 times 3 is 12. Then subtract it from 7, 7 minus 12 is negative 5. And that would exactly be how you would evaluate this. Now, a lot of that I just did in my head, which I don't necessarily recommend you do. You would probably write down those in between steps, which is what we're going to start modeling from here. But I want to give you an overview of what we're talking about today. This is in words sort of reminding you of what it means to be a variable and what it means to substitute, but at the end of the day, you're doing exactly as we did up here. You're identifying what the variable is, and then replacing that variable with your value, and then evaluating according to order of operations, aka according to that story of what's going on in that algebraic expression. The biggest thing that will be a little bit tricky as you're doing this is keeping in mind that you have to have very careful placement of parentheses. In particular, if you just write negative 3 squared and type that in exactly as is on a calculator, what your calculator is going to do is actually negative 1 times 3 squared. And what a person does, actually, that's also what that means really too, because there's no parentheses, which would end up being negative 1 times 9, which would give you negative 9. That is not the same thing as taking negative 3 all squared, which would be negative 3 times negative 3, which would be a positive 9. The first one that I wrote would not be substituting into x squared with x equals negative 3. If you're going to do that, you have to do that second one I wrote, where you actually replace that x with a negative 3 all in parentheses, or whatever it is. So let's go ahead and do some practice questions. There's sort of some worked out examples on your sheet if you want to kind of look at the notes corresponding with this video, but otherwise just jumping into the practice questions I think is good. So I'm going to do one kind of carefully again with you, and I'm going to encourage you to pause your video to try the others, but if you're already comfortable, go ahead and pause the video and try this first one as well. So for this first one, we're wanting to plug in the value x equals 8 into a couple of different expressions. The first one is x plus 3. Well, if I'm going to evaluate that expression when x equals 8, that means I'm going to replace x with the 8, drop down the rest of the expression, then I evaluate as is according to order of operations. 8 plus 3 is going to give me 11, and that would be the final value. Sort of similarly, if I have 5x, keep in mind that's secretly 5 times x when you just have the number written next to the variable like that. So that becomes 5 times, in this case 8 is the value that we're plugging in for x. 5 times 8 will give me 40. So that would be my final value. For the last one, we've got kind of two different things going on. We have x squared first, so squaring x, multiplying x times itself, and then multiplying by 3. So we're going to first replace x with his value. And even if he's not negative, I think that putting him in parentheses is just a good habit to keep in mind that whole number is what x got replaced by. And then 8 squared, that means 8 times 8, that's going to give us 64. And then to actually do out that multiplication, I'm going to write that to the side just because I like to visualize it. 3 times 4 is going to give us 12. Write down the 2, carry the 1. 3 times 6 gives us 18, plus 1 gives us 9. So our final answer would be 192. Go ahead and pause your video and try these next three examples yourself. So for the first one, we have two different variables here. For the first one, it looks like the a will be replaced by the negative 4. So I'm going to rewrite that as 8 times negative 4 because that is the value of a. The next one, the b, is being replaced by a negative 5. So that's plus 3 times negative 5. So you want to be careful about which value is being substituted into which variable. Then I can go ahead and start to evaluate further. So 8 times negative 4 gets us negative 32. 3 times negative 5 will get us negative 15. 32 plus negative 15 is going to get us negative 47 as our final answer. For this next one, we again want to substitute in extremely carefully because u is being substituted by a negative number. So I'm going to wind up with negative 2 all cubed, and then I'm going to just drop down the rest of the expression. In terms of order of operations, PEMDAS, I want to evaluate the exponent first. So negative 2 cubed. Negative 2 times negative 2 gets us positive 4 times yet another negative 2 is going to get us negative 8. Notice how I'm still indicating that in parentheses because I don't want to lose that sign that's associated with the 8. And then I do 5 times negative 8, that's going to get me negative 40. 7 plus negative 40 will get me negative 33 as a final answer. For this next one, we're actually, if you notice, replacing the exponent instead of replacing the base. So if I rewrite this expression with the x plugged in, that means 2 to the 4th power, which keep in mind very literally means 2 times 2 times 2 times 2. 2 times 2 is 4, times another 2 is 8, times another 2 is going to give us 16. For the last one, again, we want to be careful about that parentheses in terms of order of operations. So I'm going to here replace that x with a 4. Then I want to evaluate inside the parentheses first. So 7 plus 4, 4 plus 3 will give us 7. And then 7 squared means 7 times 7 to give us a final answer of 49. Oftentimes you're actually interested in doing this in some sort of real world scenario. So let's take a look at that. If, for example, we have the formula for how to convert between Celsius and Fahrenheit, here, which actually I'm noticing a little typo down here that I should really replace. That was a V here, but that's a future problem. Okay, so here, if we have this formula, C is Celsius, F is Fahrenheit, and it says convert 109 degrees Fahrenheit to Celsius, very practical problem. All you're going to do is everywhere you see a Fahrenheit in this equation, you're going to replace it with its value. Then you want to follow order of operations where you first want to do the parentheses. So you want to do 109 minus 32. That is 777. So that will end up getting you 5/9 times 77 firsts. From here you could either do this on a calculator or do it long ways. I'm going to just kind of do it the long way for illustration. So if you're doing 77 times 5, that would be 5 times 7 is 35. Write the 5, carry the 3. 5 times 7 is 35, plus 3 is going to give you 38. So you get 385 over 9. And then you might be curious to see if that actually simplifies nicely. 9 goes into 38 4 times. 4 times 9 is 36. 8 minus 6 is going to give you 2. Drop down the 5. 9 doesn't go into 25 perfectly evenly. So you're going to end up with the closest thing being 9 times 2, which is 18. So then you'd have a remainder of 7. So that would be 42 and 7/9 degrees. If you insist on converting to a mixed number, you'd probably leave it as a fraction or make it a decimal though instead. For the volume of a cone, I just replaced that C with a V for clarity's purposes, although it really could be given to you in any way. Where it says find the volume of the cone with a radius of 6 feet and a height of 8 feet. So radius is going to be this R, height is going to be that H. Hopefully that would be probably given to you and defined in the problem, but otherwise it's usually implied for these geometric problems that typically we abbreviate height with H and radius with R, just trying to keep things a little bit simple. So then you get volume is 1/3 pi 6 squared times 8. And then from here you want to follow order of operations. So you're going to do the 6 squared first is 36. And then you can just do the multiplication / division from left to right. So 1/3 times pi is going to give you pi thirds. And then if I do pi thirds times 36, well, 1/3 times 36 is the same thing as 36 divided by 3, which is 12. So we're down to 12 times pi times 8. And then 12 times 8 is going to give us 72. So this is really 72 pi. And I'd probably leave that as is. I wouldn't necessarily find a decimal approximation. And again, you can also replace values that are inside that exponent. So for example, for this Tylenol decay problem, this is what's kind of given as the formula as how much Tylenol is in your system after a certain amount of hours, let's say. So then you'd end up with 600 times 0.85, in this case after 7 hours, to the 7th power. And then this would definitely be an example that I would probably just do on a calculator from here, because while in theory we could do 0.85 times itself 7 times, I don't think that you guys probably want to try to watch me do that live on a video. So that would give you 192.35 approximately milligrams or whatever is the units in this problem being left in the system. Oftentimes for these real world formulas, you're going to have to create that yourself a little bit. So this is kind of a review a little bit of last time, but you want to identify your unknowns, and whatever is an unknown, you're going to assign a variable. And then you want to see what sort of words in the problem are sort of giving you that story of what's happening to that variable. So if you have something that, for example, says the zoo charges $4 per child ticket and $6 per an adult ticket, well, those are your two unknowns. Child ticket, which you can assign some sort of variable, probably commonly a C. Adult ticket, you can assign some sort of variable, probably commonly an A. And $4 per, that per language is really implying multiplication. Every time you see per, you should probably be thinking we're going to be multiplying values in some way. So we have $4 per child ticket, $6 per an adult ticket. And then if you want to know the total amount that was made from people visiting the zoo, you would say, oh, well, let me add that up. And then you might want to do a little sanity check to make sure it makes sense. So you might want to plug in, well, what happens if I had 3 children and let's say 2 adults visit the zoo? So $4 per child ticket, replacing the C with a 3. $6 per an adult ticket, replacing the A with a 2, to get you 24 total dollars made, which does seem to make sense. And you could even add it up the long way if in doubt. So if you have, in this case, 3 children plus 2 adults, that adds up exactly how you would want. And that repeated addition we represent with multiplication in both of these instances. Sometimes they also will give you information sort of in a business specific sense, where they might talk about fixed costs and variable costs. What you should be really thinking about fixed is that will be by itself. That's going to be a constant of some sort. By fixed costs, we mean that it doesn't change. Versus variable costs, that's where you should be thinking about that per, probably that repeated addition that would be multiplication going on. So for example, if you have a plumber that comes by that charges $480 just to visit, and then an additional $56 per hour, well, you can take 56 multiplied by the number of hours that he's working, and then add that to that initial $480 fee, and then voila, you've got yourself an expression on how much you would have to pay the plumber. And that's all, again, that's kind of recapping here. And step 3 is that you want to make sure after you sort of identified your variables, identified any information about your variables, then you want to write those expressions. And then if asked, this is sort of the new step, you'll then want to plug in at the end what it is that those values are so that you can evaluate the situation. So let's take a look at a couple examples of that. I'm going to challenge you to go ahead and pause the video and try to write this expression yourself. Then also evaluate the expression. We went over a little bit about writing the expression already, but then the evaluation in particular would be sort of the new part. So here we have a mechanic that's working very similar to the plumber that we just talked about a little while ago. So a quote for $480 for parts, that's saying that they've already evaluated how many parts they need. That's really considered a fixed cost here. Versus the variable cost is going to be that $56 per hour of labor, or an hour of labor. The reason why you know in particular that that's what we're doing with the variable costs instead of the other one is later we've identified X to represent the number of labor hours worked. So which of these varies by labor? The labor cost. If they had to given us instead, let X represent the number of parts ordered and it was $480 per part, that would be different. But instead the mechanic just said, hey, all the parts together are $480, and then this is how much I charge for my labor, which if you've ever gone to a mechanic tends to be how it works. So we'd have 480 plus the 56X, where X represents the number of hours worked. And then if the mechanic worked for a total of 5 hours, that's when you're going to take your X, replace it with your 5 hours. And then you're going to want to evaluate according to order of operations. So you first want to do 56 times 5. 5 times 6 is going to give you 30. 5 times 5 is 25, plus 3 is 280. So then you'd have 480 plus 280. And then if you do 480 plus 280, 0 plus 0 is 0, 8 plus 8 is 6, carry the 1. 4 plus 2 is 6, plus 1 is 760. So it would cost you a total of $760 to get your car fixed there. For this next one, let's go ahead and I'm going to challenge you to go ahead and pause your video, try this yourself, and then see what you get. So if it charges $21 for adult admission and $9 for each child. Here they did not give us the variables, but it's implied the adults would be one, the children would be another. Actually, they did give us the variables later. I was a complete liar there 5 seconds ago. It says C represent the number of children, A represent the number of adults. And if you want to make sure a computer doesn't yell at you, although the learning's the more important part, you probably want to use the same casing as well. So the total cost of the trip would be $21 per an adult, plus $9 per child, probably most commonly written without that explicit multiplication symbol. Then if it says determine the total bill for the field trip if 8 adults and 23 children went to the aquarium, that's asking you to go ahead and plug in what those values are. So 21 times those 8 adults, so you're replacing that A with an 8, plus 9 times those 23 children, replacing that C with a 23. And then just for the sake of time, I'm going to be a little bit lazy and do this off to the side on a calculator. So we have 21 times 8 gets us 168. Oh, I do not know how to talk today. 168. And then 23 times 9 will get you that 207. Add those guys up. And you get a total of $375 spent at the aquarium for these many adults and many children. Why there are more adults? There's more children than adults, but the costs end up being sort of similar ish between the children and adults because those children were so much cheaper.